So in the last class, we have discussed the construction of an RS flip-flop using NOR gate and discuss the output corresponding to different combinations of the input, especially 0 0, which preserves the previous state. We can call it as a memory state. When R is equal to 0 and S is equal to 1, we get 1 at the output Q, and when R is equal to 1 and S, 0 at the output, which represents a reset operation. Now, in a similar fashion, if you analyze what will be the output corresponding to input 1 1, that is, when both inputs are 1 1, what will be the output? You can see that the output will never settle to a particular value, 0 or 1. It will be ever changing. So the conclusion is that for the proper working of an RS flip-flop, you are not supposed to apply the 1 1 input, because our aim is to construct a circuit for storing a 1 or 0. So in order to work it properly, we are not supposed to apply the condition both R and S as 1, because in this condition the behavior is erratic, or we can say that condition is forbidden. Such conditions are known as forbidden state, that is, we are not allowed to make it 1. So we can say not allowed. So while using an RS flip-flop, we should be extremely careful so that such a combination will not be coming as the input. Now this is an RS flip-flop, and while drawing diagrams, you can represent it with the help of a block diagram. This is S, R, Q and Q bar. The circuits shown with actual components are known as, in electronics, such circuits are known as schematic circuits, schematic circuit diagrams. And when the circuit becomes larger and larger, it is very difficult to manage schematic diagram. So we will represent each module using different blocks. So such diagrams drawn with the help of different blocks are known as block diagram. Okay, so this is the schematic diagram of an RS flip-flop, while this is the block diagram of an RS flip-flop. Now we can see how an RS flip-flop can be constructed using NAND gate. Any circuit which can be constructed using NOR gate can be constructed using NAND gate also, as both these are known as universal building blocks. The circuit diagram for RS flip-flop using NAND gate is also same. You take two NAND gates, two input NAND gates. One of the inputs of each gate is connected to the output of the other logic gate, other output. So we can represent this as Q and Q bar. This is known as S bar and R bar. here you can notice that instead of writing as R and S, I have written R bar and S bar, which means this is an active low circuit. While the other one, flip-flop using NOR gate, is known as an active high, which means the desired state is obtained by applying a 1 and the corresponding input. For example, in order to make 1, set is 1. In order to make 0, reset is 1. Here the operation is just opposite. That is, all the inputs are inverted. So you can draw the truth table. So I will write R bar and S bar and Q. Now, in the same way as we discuss different cases of NOR gate, you can analyze the working of an RS flip-flop using NAND gate also. At present I am not going to that. You can try your own, and you can see that the slight difference. You can see that the truth table is like when both inputs are 1, you can see that it is preserving the last state, in contrast to the previous case in which 0, 0 represents the last state or no change condition, memory condition. Okay. Now, when R is equal to 1 and S is equal to 0, you can see that, okay, since this is an active low, here S bar is 0, we will get a 1 output, that is set condition. Now again, if you take this is 0 and 1, see R bar is equal to 0, it is a reset condition. So far it is fine. And the last one, 0, 0 is actually the forbidden condition in this state. In this case, forbidden. So this condition is not allowed. By using an RS flip-flop like this, we should take care that both input should not be 0, 0, because the flip-flop will not function properly. So this is forbidden condition for the RS flip-flop using NAND gate. Since it is difficult to handle these two, so while describing or while studying, it may create confusion, these two types of inputs, condition, and two types of truth table. We can modify the second one, this flip-flop, in such a way that it is also behaving like a positive or active high input circuit. It is behaving like an I flip-flop which is constructed using OR gate. How we can modify? Okay, since these inputs are S and R, complementary of S and R, in order to make it direct, we can use two NOT gates at the input side. So that will invert this S bar and R bar to S and R. Okay, we'll draw the diagram. So this is the AND gate, the feedback connection. So what we are doing is, in order to invert the inputs, we can connect to NOT gates. So this S bar becomes S here. So that, or the other way, when it is S, this becomes automatically S bar, and when this becomes R, the output of this NOT gate becomes R bar. So that it is like this. So in this case, you can write down the truth table as R and S, Q similar to the 1 in the case of NOR gate flip-flop. That is 0 0 represents no change condition, 0 1 represents set condition, 1 0 represents reset condition, and 1 1 represents forbidden state. Now we can say that this flip-flop is also an active high circuit, and we can represent this also with the common block diagram as S and R, Q and Q bar. So this is the block diagram of an RS flip-flop. So one thing that you have to notice while drawing these two diagrams is that this is a small tip. In this case, okay, this is Q and this is Q bar. The input corresponding to the flip-flop, say having output Q is R in this case, and corresponding to the Q bar, the input is S. While in this case, the input corresponding to Q is S and Q bar is R. Why this is like this? So that you can understand when you analyze the working of the flip-flop using the techniques that we have already discussed. And now we will discuss the construction of a clocked RS flip-flop. Clocked RS flip-flop. So clocking is actually a modification to the conventional RS flip-flop. So before going to the details of the circuit, we have to understand what is meant by a clock. A clock is also referred as enable. Abbreviations are CLK or say EN. So what is a clock first? Then we can discuss what is the purpose of a clock. Clock is actually some signal used to synchronize when there are large number of digital devices in a circuit. We know that in a computer usually there are large number of components like flip-flops, registers, half order, full order, so many circuits. So in order to synchronize the operation of all this, a clock is used in a digital system. You might have seen that usually there are two parameters associated with the specification of a computer. One that we have already discussed, that is the word length, that is size of the register. We usually refer a system as consisting of 64 bits, 32 bit, 8 bit and so on. We have discussed that in the case of when we studied the number systems. Another parameter associated with the specification is the speed. Speed is usually designated with a frequency of the order of say a few gigahertz or something like that, 1 gigahertz, 2 gigahertz, 2.5 and so on. Actually, what is this? This is actually representing the clock frequency inside the system. So the clock is actually running to all components so that the operations of the different units in a computer are synchronized. So this is basically an additional control over different circuits. Actually clock is a square wave. Frequency of the square wave is actually represented as the clock speed. So the system is designed in such a way that certain operations are performed during some half cycles, certain operation during other half cycles, and so on. So this is like a heartbeat in human body, which is synchronizing all the operation of the different components in a computer. So clock is used for synchronizing all components, all units in a digital system. Synchronizing all units in a digital system. So clock is actually varying between two levels, 0 and 1. For certain amount of time it is 0, for some other level it is 1, again becomes 0, and so on, just like any other square wave. Now how we can incorporate a clock or an enabled signal into the existing flip-flop. For that again we can take a flip-flop using NOR gate. Okay, so this is a flip-flop using, so this is Q and this is Q bar and this is R and this is S. Now what we can do is we can connect two AND gates, Okay, I will draw the diagram here. This is Q bar, this is the existing R and S. Now we can connect two AND gates, each of two inputs. So one input from each AND gate is joined together, which serves as a clock or enabled signal, and the other is again we can represent as R and S. So using a block diagram also you can draw this same thing. You can draw two input AND gates joined together, one input each. So this is the final R and S, and this is the enable, Q and Q bar. So what is the working? What is the function of this enable? By looking into this you can see that these two are two AND gates. So according to the property of an AND gate, the output of the AND gate is a 1 only if both inputs are 0. That means if this enable is equal to 0, whatever be the inputs R and S, output of these two AND gates will be 0. So we can say when enable is equal to 0, irrespective of R and S, the actual input of the RS flip-flop remains 0. So this is actually a disabled condition. You can draw the truth table. Now we have to draw three inputs: enable, R and S, secure. So when enable is equal to 0, whatever be the input R and S, if it is 1 or 0, that doesn't make any difference. So you can put X. It retains the last state, that is no change. NC stands for no change. So we can say that the flip-flop is in the disabled condition. The changes in the input will not affect the output. Now if you make 1, enable 1, if you make this 1, you can see that output of these AND gates, whether it is 1 or not, depends upon the second input. So we can write down here, when R is equal to 0 and S is equal to 1. See, S is equal to 1. Two inputs of the lower AND gate becomes 1, so that the output becomes 1, S. So this S becomes 1. While since R is equal to 0, even if it is 1, output of this AND gate is 0, that is, this R is equal to 0. So this is 0 and this is 1, which is corresponding to set. Similarly, if you take enable 1, R1 and S0, you can see that the upper AND gate is, output of the upper AND gate becomes 1, because this time both inputs of this AND gate are 1, so that the output becomes 1. So R is equal to 1 while this is equal to 0, so that this represents a reset condition. Now as usual, if both are 1, it is, you can see it is forbidden state. It's not allowed. So this is the working of a clocked RS flip-flop. Similarly, we can construct a clocked RS flip-flop using NAND gate also. So we'll draw the diagram of NAND gate circuit. So NAND gate circuit. Okay. Now there is an advantage. You can see that this is actually R and this is S bar and this is R bar. And in order to make it S and R, we have used two NOT gates. And we have to use two AND gates for making an enable, connecting an enable line. So combining that AND and NOT gate, we can replace this AND and NOT gate by a NAND gate. So we can use two NAND gates. So AND plus the NOT, which is used for inverting input to make it as RS flip-flop instead of R bar, S bar flip-flop. You can see the previous diagram. So this is again an enable or clock. Both terminologies can be used. In some books you can see that it is written as clock. That depends on how we are using this. So this is S and this is R. So these are the circuit diagram of a clocked RS flip-flop. Clocked RS flip-flop. So the advantage is that if there are a number of RS flip-flop used in a circuit, this enable or clock can be join together to form to function all the units simultaneously. That is known as synchronization. So the truth table is like this. You can represent this using a block diagram. The block diagram of a clocked RS flip-flop is like this. Two inputs, S, R, and this is the enable line, Q and Q bar. So we know that this is working when the enable is 1. So this is a level triggered one. Such circuits are usually known as level triggered one. That is, this signal is working or the system is enabled when this enabled signal is a 1. So it is a level triggered with level of 1. Or this is also an active high circuit because enable is working when enable input is 1. So corresponding active low circuits are also there. Just by putting a NOT gate also at the enable side, that will become an active low circuit. So a clocked RS flip-flop with active low enable signal or active low clock is represented with a bubble at the enable side, and usually EN bar is used. S, R, Q. So usually active low signals are represented with a bar on the variable name, and it is active high, it is written directly. So these are the block diagrams of clocked RS flip-flop, which is active high and active low, Q, Q bar, Q and Q bar. So okay, I have written like this here. Again, we can come to the truth table of an clocked RS flip-flop to study further modification of the RS flip-flop. I am writing this is 0, XX, no change. When enable is equal to 1, 0, 1 represents set state, enable is equal to 1, 1, 0 represents 0 state, and 1, 1 is forbidden. Now you can see that this forbidden state should be completely avoided. Okay. Now when enable is equal to 0, whatever be the input, it preserves the previous state. Now when you want to change the output to set or reset a flip-flop, what you have to do is you have to apply enable signal as 1 and make R is equal to 0, S is equal to 1 for setting operation. The opposite, R is equal to 1, S is equal to 0 for reset operation. So when we want to change the state to store either as 0 or 1, you can see that the output is, so the input is always complement of the other. To set S1 R0 and just opposite, that is for resetting R1 S0. So you can combine this both R and S together so that one is always the complement of the other, so that we can reduce one input from the conventional RS flip-flop. How is it possible? How is it possible? We can draw an RS flip-flop. This is this is R, and this is N. How we can change? Because R is always the complement of the S input. You can derive the R input using a NOT gate. So R and S are combined to form a single input. So you can call this combined input as D. So this modified flip-flop has only 2 inputs instead of the 3 inputs in the previous clocked RS flip-flop. The 2 inputs are, one is D, the other is the enable signal that we have already mentioned. Such a flip-flop, modified flip-flop, is known as D flip-flop or D latch. It is also known as a latch. In fact, this is the basic unit of a register, basic building block of a register, because we don't have to change 2 inputs for changing a state, that is combined to a single one. So D stands for data, so it is a data latch or data flip-flop. So in order to construct a 4-bit register, we have already discussed that a register is actually a combination of flip-flops to store a binary number or data. So a binary number can be stored using a number of flip-flops. So an 8-bit register consists of 8 flip-flops or conveniently 8 D latches. And if you have to construct a 64-bit register, you have to use 64 such D flip-flops. For the convenience, we can discuss a 4-bit register. You can extend this to any number, 4-bit register. So in order to construct a register consisting of 4 bits, you have to use 4 D latches. If it is 8-bit register, then you have to use 8 latches and so on. Okay, so I have taken 4 D latches and all these have inputs. These are the D inputs. We can call this is the D of the first one, D second, D third, D fourth. So we can call this as D0, D1, D2 and D3. Since these are D latches, one more inputs are there, which is the enable. Enable and so on. How will you connect this enable? Already I have mentioned that the purpose of this enable signal is for synchronizing the operation of different units. So obviously what we have to do is you have to interconnect this. You have to join this. So it is coming to, we are taking it as a common input. We can call it as common enable input, enable or clock. Now the corresponding outputs, you can call it as Q0, Q1, Q2 and Q3. Okay, at present there is no significance for mentioning the Q barred inputs. It is also there, but we don't have to take it at this time. So this is the construction of a 4-bit memory unit. So how we can store a particular data in this? What is the process? Suppose you have to store a number, say 1011. So if you have to store a 1011 here, what you have to do is you apply 1 here, apply 1 here, apply 0 here, apply 1 here. So D0 is equal to 1, D1 is equal to 1, D2 is equal to 0, and D3 is equal to 1. 1, 0, 1, 1. So usually this is kept as 0. So since this is equal to 0, the changes that you are making here will not appear here. So after making all the values here, after setting all the values here, you have to make this 1. When this enable is changed to 1, you can see that all the latches will be enabled, so that this 1 will be transmitted to the output. This will become 1, this will become 1, this will become 0, and this will become 1. Usually a circuit will have, it will take a finite amount of time, even though it is very small, for settling the system. Now you can remove, after that time, you can remove this to 0, so that this value will remain here without any change. Even if you change these values, because when enable is equal to 0, the output will be kept constant without any change, irrespective of the inputs. So we can say that this is in the memory state. Now this register is storing the data 1011 in its memory. So when you have to change the data, suppose you have to change it to, say we have to change it to 0010. What do you have to do? You make this 0, this 1, make this 1, 0, this also 0. So whatever is the output required, you have to change the input in the same fashion, then set the enable to 1, so that the data will appear here. And now, in order to make it permanent, you can change this to 1 and then 0. So when you make this to 0, the data will be intact. So whenever you have to change the data, what you have to do is, first you apply the desired values at the corresponding input, enable this, that means make this 1, and then after a particular time you change that to 0, so that the value will be kept intact. So this is the concept of a register. So in computers, the registers are usually constructed with the help of such flip-flops. So this is register using registers using latch. Another modification that we are going to discuss is the modification method used in the synchronization or clocking mechanism. We have seen that a clock consists of a series of square waves. So this is level 0 and this is level 1. Level. So this is level 0 level. This is level 1 or high. Okay. Now the clocking mechanism that we have discussed in the earlier case is a level triggered one. That is, the enabled signal is active as long as the enabled line is A1. എത്ര സമയം എനേബിൾ സിഗ്നൽ ഹൈ ആയിരുന്നാലും ഈ എനേബിൾ വർക്കിംഗ് ആയിരിക്കും. So a further modification is incorporated so that it is not active for the complete duration of a clock. Another modification is done so that it will respond only to any of the edges of the square wave. So what is meant by an edge? Such circuits are known as edge triggered flip-flops. The previous one is known as level triggered one. The one that we have already discussed, that is when the system is enabled when the clock or enable is equal to 1 or 0, is known as a level triggered flip-flop, while a flip-flop designed in such a way that it will respond only for any of the edges is known as an edge triggered flip-flop. Edge means you can know that, you can see that it's a square wave. A square wave consists of two edges. One is a positive going edge, that is the level is shifting from 0 to 1. So this is positive edge, while the transition from 1 to 0, this point is known as negative edge. So in a clocked flip-flop, we can incorporate additional circuits so that it will respond only in one of these edges. Such flip-flops are known as edge triggered flip-flops. So an additional circuit is used. We are not going to the actual details of the circuit, but we can represent it as a block and we can write it as an edge detection circuit. So we can take an RS flip-flop, a normal RS flip-flop, clocked RS flip-flop, and the enabled signal is connected with the help of, this is the actual enable, with the help of an edge detection circuit. Edge detection circuit. So if you connect an edge detection mechanism or edge detection circuit, this is known as an edge triggered flip-flop. Since there are two edges, you can use two types of circuits, either an edge detection circuit for detecting positive edge or for negative edge. So depending upon the type of this circuit, edge detection circuit, there are two types of clocked flip-flops known as negative edge triggered flip-flop or positive edge triggered flip-flop. A positive edge triggered flip-flop will respond only during the positive edge, that is when the signal is making, the clock is making a transition from 0 to 1. It will not respond, or it will be in the disabled state when the signal is remaining 0, when the signal is remaining 1, or when the signal is making a transition from 1 to 0. So it will respond only for this edge. Similarly, a negative edge triggered flip-flop will respond only for this edge. It will be disabled for this level, or this one. So this is the concept of a level triggering, an edge triggering mechanism. So there are two types of edge triggered flip-flop. We can represent that with the help of a block diagram as this is S and this is R, Q and Q bar. So this is the enable. How we can represent or distinguish it from the ordinary level triggered flip-flop we have discussed earlier by putting a triangle. So a triangle, a small triangle at the input represents the clock edge. So this is S and this is R and this is enable Q bar. So this is a positive edge RS flip-flop. Actually the name is positive edge triggered. Similarly, we can represent a negative edge triggered RS flip-flop as S and R. How will you represent? All negative signals are represented with a bubble. So you can put a bubble. A bubble represent. Bubble with an arrow represent a negative edge triggered RS flip-flop. The same modification we can do in the case of a D latch also. So this is the D input. This is positive edge triggered D latch. And this is negative edge triggered D latch. Now, what is the truth table of a positive edge triggered RS flip-flop? Truth table. That is also important. How we are representing an edge in a truth table. If you put 0 or 1, that represents a level. Both these represent a level. So how we can represent an edge in this case? So edge is usually represented using an arrow. So we can see that when this is equal to 0, whatever be the input, it is no change. Similarly, if it is 1, then also there is no change, because we know that for a positive edge triggered RS flip-flop, it will respond only for the positive edge. So a positive edge is represented with an up arrow, just like this. So in this case, if 0 1, this is 1, 1 0, it is 0, 1 1 is forbidden. Similarly, if it is negative, if it is a down arrow, then also there is no change. I will draw that in the next paper. Okay, I will draw it once again. If it is 0, whatever is the input, no change. And if it is 1, then also no change. And if it is a negative edge, then also no change. And change is only when it makes a positive transition or positive edge, and the clock makes a positive edge. So in that case, 0 1 is set operation, 1 0 is reset operation, and 1 1 is forbidden. Similarly, here everything is reversed. Enable R and S Q. You can see that 0, okay, there is no change. 1, then also no change because it is edge triggered, and up arrow no change, and change is only when makes a transition from 1 to 0, negative edge. 0 1 is 1, 1 0 is 0, and 1 1 is forbidden. Similarly, in the case of D latch, positive edge, negative edge. You can draw enable. Usually this is represented with a bar symbol in the case of negative edge. R and S Q. Sorry, in this case we need only D. It is D latch. So 0 X no change, 1 X no change, negative edge X no change, but positive edge 1 becomes, output becomes 1 for D is equal to 1, and output becomes 0 when D is equal to 0. And here enable DQ for the negative edge. Similarly, you can write 0x no change, 1x then also no change, positive edge no change, change is only for the so this is the concept of edge triggered flip-flop in the case of both RS and D flip-flops. Now there are further modification. There are different types of flip-flops starting from RS. We have studied two variations, mainly RS, and from that we have designed D flip-flops or D latches. And there are much more varieties of flip-flops for different applications. One of the main type of flip-flop that we are using commonly for different applications is known as a JK flip-flop. Now we are not discussing this, but you have to do practicals using the JK flip-flop. So if necessary, you can discuss then. Otherwise, you can refer some books. As far as the theory part is concerned, our syllabus is restricted up to this D latches. Okay.